Ecological modelling, like food webs, are a pretty big deal these days, as understanding them can aid in the whole manner of issues coming our way. More mouths to feed, extinction rates growing daily, and the ubiquitous issue of climate change. However, it ultimately all comes down to tracking one key resource: carbon. Food webs are essentially just tracking carbon going in and carbon going out, and understanding this flow and its nuances can allow us to identify and tackle these issues into the future. And at the moment, there's no better way to do this than with Ecopath. Ecopath is an ecosystem modelling program that allows for a comprehensive examination of an ecosystem and all of its synergistic interactions. It enables the quantification of organisms that utilise a similar ecological niche or functional group into a trophic level within their ecosystem based on what they eat and what they are eaten by. Examples include herbivorous fish and cephalopods. Estimates on abundances of populations can be established. For example, if a certain number of predators exist in an area, then we know that there must be a certain population of their prey in order to sustain them. Using 6 parameters and 2 master equations, Ecopath creates a static simulation of an ecosystem in which mass and energy are balanced across biomass pools into a cohesive model of a single point in time. Under the assumption of ecosystem equilibrium, in which neither biomass production nor loss overtakes the other, Ecopath can thus provide us with an estimate of the biomass budget of the modelled ecosystem, essentially allowing us to see where the biomass is and in what quantities. The 6 parameters of Ecopath are biomass, estimated by the counting of samples or existing literature; mortality and diet composition, both estimated via stomach contents and a group's energetic requirements; consumption, established from methods such as oxygen consumption or the aspect ratio of a fish's caudal fin; harvest by humans in fisheries, accessible in fisheries data; and ecotrophic efficiency, the amount of biomass originating from the ecosystem in question and not accounting for gains or losses through factors such as migration. The 2 master equations are production equals catch plus predation plus net migration plus biomass accumulation plus other mortality, and consumption equals production plus respiration plus unassimilated food. With these parameters and equations, Ecopath can get stuck into the modelling of the ecosystem. But which ecosystem to model? Smiths Lake in northern New South Wales is a prime spot for examining beautiful scenery as well as Australian ecology, and it provides fantastic data on biodiversity, abundance, and more. Smiths Lake is an ICOL, or an intermittently closed and open lake lagoon system, which is completely different to this river you see behind me. Why did we come down here then? Smiths Lake routinely opens and closes to the sea, creating fluctuations in temperature, salinity, and stock replenishment. Ecopath's application has shed some light on a variety of the trophic groups present, including birds, large fish like bream, small fish like hardyheads, herbivorous fish like luderick, benthic fish like flathead, as well as squid, crab, bivalves, amphipods, barnacles, zooplankton, phytoplankton, seagrass, detritus, and more. However, there is one dominant group that is throwing the Ecopath program out of sync. Jellyfish have a problematic overabundance that is affecting the interpretation of data used by Ecopath. In the 2020 estimates of biomass, they account for 65% of it, and the initial guess of 570 tonnes of jellyfish biomass is believed to be a gross underestimate. The 2015 value of 0.1 grams per metre squared was reduced arbitrarily from 17, as this was considered too high, yet was later eclipsed by data from later years. 20 times more zooplankton than was estimated to be in the lake would be needed to sustain the jellies. The ecotrophic efficiency value should be a perfect 1 for the jellyfish, considering they're not exactly known for their vast land or sky-based journeys, whereas seabirds, such as the migratory swans that visit Smiths Lake only occasionally, should have a lower value as they bring in and leave with extra biomass. However, this had to be arbitrarily reduced to 0.3, and other jellyfish data altered in order to not disrupt the rest of the model. Jellyfish abundance has increased dramatically since 2017. 2019 and 2020 having the highest overall abundance figures at 50 and 60 grams per square metre respectively. 2 species of jellyfish inhabit Smiths Lake, Philorhiza punctata and Catastylus mosaicus. Both prey on zooplankton, however Philorhiza has photosynthetic symbionts. Specimens of both species are sampled at Smiths Lake and divided into size classes. The majority of these were medium-sized in 2019, yet in 2020 were smaller in size than both of those previous years. Zooplankton, the primary prey of jellyfish, had its highest abundance value in 2018, before the leaps in jellyfish biomass in 2019 and 2020. Is it possible the booming jellyfish levels in these years are the result of the vast increase in zooplankton abundance in 2018? With such an abundance of jellyfish nibbling away at these poor little organisms, thus being responsible for their decline in 2019, in some sort of feedback loop. But then how could the 2020 jellyfish abundance be at its peak without enough zooplankton as prey? Something else may be at play here, and that something is temperature. Researchers found that jellyfish often respond well to and bloom in warmer conditions that are exacerbated by climate change, leading to an ongoing jellification of waterways around the world. Australia's hottest year on record, at 1.52 degrees Celsius above the national average, was 2019, the same year jellyfish abundance spiked. Are the mounting temperatures facilitating jellyfish expansion on a yearly basis? Though the majority of jellyfish collected in 2019 were of a medium size, their growth perhaps fueled by the peak zooplankton biomass of the previous year. In 2020, jellyfish abundance peaked, and the majority of them were of a small size class. Perhaps the warmer temperature conditions facilitated jellyfish reproduction in an exacerbated bloom of sorts, leading to an increase in smaller and presumably younger jellyfish individuals. Could the temperatures potentially reflect higher sunlight levels in 2019 that may have aided the photosynthetic symbionts present in Philorhiza, leading to an increase in their species abundance exclusively? Lack of distinction between the two species is a confounding issue, and to precisely determine the nature of Smith's Lake jellyfish explosions, more knowledge on the growth and reproductive rates of these jellyfish across both species is needed. Now, these jellyfish are not a problem unique to Smith's Lake. Jellification in the oceans and blooms of this pesky translucent invertebrate is another story altogether, and another case where Ecopath has proven its use. In the Irish Sea, jellyfish abundance has increased and is positively correlated with higher sea surface temperatures, with biomass believed to have increased due to climate change since 1970. Similarly, in the East China Sea, large jellyfish blooms have occurred in response to changing climatic circumstances and overfishing. An Ecopath model was created to simulate the ecosystem and included 45 functional groups. This Ecopath revealed that jellyfish blooms were facilitated by overexploitation of a fish variety called Stromatidae, which competes with and predates on jellyfish. Identification of this trophic interaction via Ecopath illuminated a way forward in the East China Sea that can allow for the management of both fish stocks and jellyfish blooms. So, to the people worried about the protoplasmic jellies, furthering our understanding of ecosystems through modelling such as Ecopath may hold the answer in tackling them and other issues, and may help us before we end up like Marlon and Dory. Thanks for watching.